And I'm not sure how far we'll get. We might even actually get out early because of what kind of where I wanted to stop. So tomorrow we are set to look at the periodic table in lab, so that should be good. But in the meantime, we've talked about elements of the periodic table. We need to kind of delve into kind of look at the atom a little closer. And what I think is neat about, all matter is made up of atoms. So atom is a big, hairy deal, right? So we kind of got to, in order to understand matter, we need to understand the atom. And a lot of times students come to this class and they already have a sense for it. Basically, what you probably think of an atom is something kind of one of these two models down here. The idea of we have a nucleus, that's that yellow thing, and then these kind of balls here are the electrons, okay? Actually, in this one, which is even a little more sophisticated of what an atom is, these little dot, dot, dots are electrons, and there's a nucleus hiding in there. But we didn't always know that. And the video we watched on Monday kind of talked about clear back, was it Democritus or something, came up with the idea of the term atom, actually. But not as late as Democritus actually was Dalton. And Dalton was that, he was in the 1800s, and he was the dude that was colorblind, and he kind of came up with something called Dalton's atomic theory, and we'll be looking at that. So Dalton just simply said an atom looks like, he just kind of came up again with the idea of all matter is made up of little particles called atoms. And then Thomson, you can read in your textbook a little bit more of details about this. Thomson actually ran some experiments, and he said, well, an atom actually has charged particles within the atom. And he didn't kind of break up the atom as we know it today with the nucleus and electrons outside, but he said basically the electrons and protons are kind of, it's called the plum pudding model. Okay, I think that's kind of neat. And then Rutherford, that was a big hairy deal. Can you kind of see that dark purple in the center there? That would be the nucleus. And then kind of the light purple around it would be where the electrons are. And one of the things we're going to talk about is electrons actually are in what we call a cloud outside the nucleus. Okay. So then with Bohr, he actually took it up a notch. And then one of the things I like about science is being shown here. Basically, we kind of piggyback on what other scientists what other scientists knew. We don't start from scratch. But we're going to spend some time talking about electrons, actually I think in this unit of material. And these, like I said, this is the nucleus, which we all know and love, kind of that dark sort of yellow. And these are electrons. And so what Bohr said is that actually electrons that are in a cloud outside the nucleus, they aren't all created equal. Okay, we actually have an electron that's here, an inner electron, and we have electrons that are outer electrons. And so we'll kind of talk about how electrons are organized. So that was a big hairy deal. And then bumping up one more notch, Schrodinger, he came up with the idea, he kind of went further with the concept of electrons being kind of a cloud, electron cloud. And so instead of having discrete little electrons, like you have an electron here, an electron here, the problem with Bohr's model is it almost looks kind of like the solar system, where the nucleus is the sun, and then kind of the, because of gravity, because that's why planets orbit the sun, because of gravity, electrons kind of orbit the nucleus, and that's not really the right deal. What Schrodinger said, and it kind of makes me itch sometimes, is basically, if you're familiar with, if you watched Breaking Bad, one of the people on Breaking Bad, his nickname is Heisenberg. There's something called Heisenberg's uncertainty principle. So what Schrodinger said is it is uncertain, it is definitely uncertain where those electrons are. Not only actually where they are, but what energy they have. You cannot know both of those pieces of information about an electron. So that's the Schrodinger model. Okay, so back to Dalton. Again, he wasn't the first person to come up with the concept of an atom, but he kind of, I think, brought it up again. And you're going to see some color. Hopefully you're not colorblind, so you can see some color on this slide. The blue actually are part of Dalton's original atomic theory, and they are wrong. Okay, so the blue is wrong. So in other words, all matter is made up of atoms, okay? But those atoms are indivisible and indestructible. Indestructible, okay? And that's not true. Okay, actually, we know that atoms can be split and release a lot of energy. The other thing Dalton in his atomic theory said, and actually you have a homework coming up here in a minute to kind of revisit this slide and answer some questions about Dalton's atomic theory, is he said that atoms of the same element are identical in chemical properties, which is correct, but he also said that atoms of the same element all have the same mass. And one of the things we're going to talk about Friday is this concept of an isotope. And so actually, you might already be familiar with the concept that carbon has different isotopes of carbon, but they are chemically the same, they do not weigh the same. He goes on to say that atoms of different elements will have different masses, and if they're different elements, their chemical properties will be different. And that's true, that's good. Okay. In the next unit of material, I think we're going to talk about compounds, how atoms of different elements join together to make a repeating unit, a compound, like water is a compound. But Dalton said that actually compounds are formed by atoms of different elements. Now notice there is something blue there, which means that that was not correct in his original atomic theory. I can go a couple of ways with this, but actually you can, if you go into study life molecules, they can get very, very large. And so, we're familiar with, H2O, where 2 hydrogens and 1 oxygen. It's possible to have a hydrocarbon that has, 71 carbons, 93 hydrogens, and 21 oxygens, okay? I just didn't make that up. I hope there's a compound out there like that. But especially molecules that are associated with life can get very large. The last one actually has some red there, and the red in this case is if we were to take his original statement, atoms are neither created nor destroyed, it would be correct if we added the thing in red, which he did not originally have. And this actually kind of goes back up to the first thing on this slide. So atoms actually can be created and destroyed if you go into extraordinary means. That would be some sort of nuclear chemistry. So during ordinary chemical reactions, like in the chemistry lab, we'll be counting on the fact that atoms are not created or destroyed, but no nuclear chemistry in our lab. So in physical science, or just in science, or just in this universe, I just think it's wonderful that we definitely have this theme of conservation going on. And kind of the theme of conservation of matter can be thought of as in many ways. Atoms are always conserved, matter is always conserved, and mass is always conserved. By that I mean that during ordinary chemical processes, you're not going to create those things, and you're not going to lose those things. I think it's neat to think back, before the time of Dalton, or even in the time of Dalton, the fact that the physical world was not nearly as well known, obviously, as it is now, and they did not. This tenet was odd to them. They thought that matter could come and go, and so I think that's kind of cool. Okay, so we'll take a quick look at these. These will be due, and we'll get to the next assignment slide right quick too. These will be due on Friday. Fabulous Friday. We don't have class Friday. These will be due on Monday. Thank you. Oh, thanks.
She's like, I'm not coming.
So like I said, these you read in your textbook, and you can go back to the slide that I had too, but these are all questions about Dalton's atomic theory. So, okay. So, all right, continuing to look at the atom. Now this is actually Thomson's plum pudding model, so kind of just a random figure from your textbook, where Thomson recognized, unlike Dalton, that actually atoms were made up of, within an atom we had positive and negative charges, but he thought that they were all together. Okay. I meant to bring a BB to kind of make this more alive. Okay, but if you think of the size of a BB, and if you were to kind of put it on the floor, okay, that BB could represent the nucleus of an atom. And then actually to get to the nearest electron in a cloud outside the nucleus, you'd have to go about 5 stories. Okay, so about 5 stories up, 5 stories down, 5 stories side to side, and you figure stories maybe 10 feet. Okay, so that is kind of scaling up the nucleus. Now the reason that seems crazy, like 5 stories, is basically in relative sizes, the nucleus is very, very, very small. Okay, so I just think that is so cool. So one of the things you need to know for this class is kind of a little bit more about the 3 main subatomic particles. Now, if you take a physics course, they might go into more smaller pieces than just these subatomic particles. But you just need to know the protons, the neutrons, and the electrons. And actually, there's this thing called a particle collider that takes ordinary matter and makes ordinary matter smash together, and it breaks down into even smaller pieces. Okay, so here again is kind of the yellowish sort of thing is the electron cloud. Okay, oftentimes for the nucleus, you'll see actually a couple of different colored particles. In the nucleus are the protons and the neutrons. And remember, we talked the other day, we're going to see it here in a minute, that protons, they're all important, honestly. But protons, actually, that is I usually call it the whole number on the periodic table. Okay, so, the periodic table is arranged with elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, blah, blah, blah. And those whole numbers are the number of protons, the nucleus of those sort of elements. So this is a thought from your textbook. If you were to take a grain of sand, so just pick 1 grain of sand, okay? And of course, all matter is made up of atoms. So if you were to take the atoms in 1 grain of sand and scale up the atoms to the size of the grain, basically that new volume would be the size of a mountain, Mount Everest. I think that's kind of a strange way to think about it. But so you take a pebble, it's made up of atoms. Atoms are very small. Scale those atoms up to the size of the pebble, and now you have Mount Everest. So here's my list of things you need to know for the 3 subatomic particles that we are concerned about. You need to know protons are positively charged. You need to know where the protons are found. They're in the nucleus. So on your Unit 2 exam, I'll be asking you questions about these 3 subatomic particles. The protons in the nucleus help to kind of shepherd the electrons, help make sure the electrons are associated with the atom. It's because like repels like, and unlike attracts unlike. So actually the electrons are attracted to the protons in the nucleus. So the other particle that is in the nucleus are the neutrons. And these 2, let's see, how do I say this? Okay. Actually, it's not listed here, but kind of that 3rd bullet right there, this one right here, wait, the 4th one. This one right here, the 4th one. Actually, we say the proton has significant mass. Of the 3 subatomic particles, we're going to see basically the electron is, for our intents and purposes, massless. Protons have mass, neutrons have mass. Okay, and then the last one, all it's saying is, the last one is just saying, for instance, if you just randomly say, I have an atom and it has 80 protons in it, what element is that atom? Well, you'd find 80 on the periodic table, and you would know the identity of that element. That's it. And one of the things I teach in the fall is astronomy, and we talk about stars, how stars actually are shining because of nuclear fusion. Basically, they're making heavier and heavier elements. So as they, under great temperatures and pressures, go ahead and make an atom with more protons in their center, that atom becomes a new element. I think that is so cool. Okay, so you'll need to know a little bit about neutrons. Neutrons are neutrally charged. Neutrons have no charge. They are found with the protons in the nucleus. Now, I said that like repels like, so if you think of the nucleus and those protons, in the case of Mercury, you think of 80 protons in the nucleus, and they will repel each other. Actually, the neutrons in the nucleus of that Mercury atom, kind of like Switzerland, they kind of give a little space between those positively charged protons. So they kind of act like glue and help the protons coexist. Okay. So that fourth one up there, again, the statement I made about protons also applies to neutrons. They have what we call significant mass. And here in a minute, I'm going to kind of tell you how much mass it has. All right. The last one we're concerned about are the electrons. And like we know from Bohr and Schrodinger, the electrons are actually outside the nucleus. We know from Schrodinger they're actually in a cloud. They're negatively charged. They're outside the nucleus. And if you think of the whole BB being the nucleus and then 5 stories up, 5 stories down, 5 stories side to side being basically the location of the nearest electron, it's basically that electron creating that electron cloud that gives an atom its volume. Because you know it's not the nucleus. So that's pretty cool. When we talk about compounds, like water, and when we talk about chemical reactions, we're going to see that when matter reacts or combines to form compounds, it's the electrons that actually reach out and do the swapping, or electrons are transferred or electrons are shared. So to me that kind of makes sense. The nuclei, the nucleuses, the nuclei of all the atoms basically stay intact. It's the electrons that are involved in making compounds and chemical reactions. Okay. And if I were to animate this, basically what you would see is kind of this, I don't know, you see kind of green and blue in here. That's your nucleus, your protons and neutrons. If I were to animate it, it's kind of a dumb animation. Basically, it just kind of shows those electrons kind of buzzing around. When you see a picture like this, it doesn't mean that each particle represents a particular an electron. It just says basically we're not sure where the electrons are. Doesn't mean that scientists haven't found it yet. It just means it can't be done. Okay, Heisenberg says that you cannot know both the location and the energy of an electron at any given time. And they don't orbit like planets. It's actually an electrostatic sort of attraction to the protons. Okay, so here we have the Christmas thing in the middle, red and green, of course, the 2 particles in the nucleus, the protons and the neutrons, and the electron cloud outside. Cool. So this is kind of weird, okay, to think of like how very much a proton, how small the weight of a proton is. Okay, now this is in kilograms. Okay, this is how much a proton weighs. Of course, this is how much a neutron weighs, and this is how much an electron weighs. They are going to they are drawn to scale so that they all have the same scientific notation, the same exponent, but you can kind of see already that this is significantly less than the neutrons or protons. Electrons are what we kind of say, like I said, as far as chemists are concerned, electrons are massless at this level anyway. Well, kilograms is not a very good way to weigh. It's not a very good mass to use to weigh atoms. So instead of that, scientists introduce another mass. And the other mass scale is actually atomic mass units. Okay? AMUs stands for atomic mass units. And these days, I say chemistry doesn't change. I don't know why they change textbooks on us. But these days, actually, instead of AMUs, we simply use what I've seen, the symbol U for AMUs. So if you were to say how much the proton and neutron weighs, to me, if you're going with just, two significant figures, three significant figures would be different, but I would say they weigh about 1 AMU. They both do. And this one, massless. I'm sure my physics friends would disagree. So the cool thing is, and this makes sense, right? Kind of. If you were to, we're going to talk about the elements, and at some point soon you're going to be able to say, oh, carbon, how many protons, how many neutrons, how many electrons. But if we just pick on carbon, okay, carbon is number 6. So we know the number of protons is equal to 6. There are various forms of carbon, so they kind of vary by neutrons, but we'll just go ahead and go with this version. 6 neutrons for carbon, and if it's neutral, actually we're going to have to go with 6 electrons for it. Okay, so now here's the cool thing, is if you actually want to go ahead and add up, basically take 6 times 1.0073 AMUs plus 6 times 1.0087 AMUs plus 6 times 0.00055 AMUs, you would get how much a carbon atom weighs. I think that is so cool. But here's the catch. And you can do the math. And actually what you'll come up with is that particular carbon atom that has 6, 6, and 6, actually it would weigh less than, the mass says. And there's this thing called binding energy that keeps a carbon atom together, and a little bit of that mass is converted to energy. That's so cool. That's so cool. So, it's always we always talk about matter is not created or destroyed, but Einstein says you can actually convert matter to energy. This is what stars do. You can take a certain amount of matter and you can convert it to energy, and it looks like this. They're related by c is the speed of light squared. So that's binding energy. Anyway, the last column then actually just says what the charge is. So sometimes on my answer keys, when I am talking about protons, I would give the symbol P with a plus sign. Sometimes when I'm talking about neutrons, I'll go to the symbol N with a superscript 0 because they're neutrally charged. And of course, electrons, I'll do the letter E with a superscript negative for electrons. Very good. 3 subatomic particles we're worried about. So we'll take a look at these right quick. These look like this. Okay, so it's I like it. It's a good homework. These are all questions about the electrons. These are all questions about the protons. Okay, these are all questions again about electrons, and these are all questions about protons. So hopefully, I hit the highlights about the subatomic particles on, each had its own slide, but we should be able to answer these just fine. And for the previous homework, you're supposed to explain why your answer is, and for these, you just have to say what's true and what's false. Okay, so those will also be due on Monday. Okay, and that's how far I wanted to get. I know we're getting out early again, but I don't know if I'm talking too fast or what. I kind of want to break here because on Monday I want to talk about kind of different versions of the same element called isotopes.